Hello, my name is Robert and welcome to our presentation on our entry to this year's Light Aircraft Design Competition. We are a team of aeronautics students from Imperial College London. Due to the present circumstances, we have adapted to work across 3 different time zones up to 7 hours apart. The design was completed over the summer. I will now pass on to Ryan from our team, who will now explain the design.
The Vertical Takeoff Lifesaver concept, or VTOLS, is a VTOL air ambulance with a range of 337 kilometers and an economical cruise speed of 88 knots at 1,000 feet of altitude. The 3-view drawings shown here are of the aircraft in the cruise configuration with gears up and front prop rotors retracted. The aircraft has a length of 11.05 meters and a wingspan of 21.46 meters. It features joined tandem wings, each set with an aspect ratio of 45, retractable front prop rotors to prevent turbulent flow hitting the laminar wings, a hybrid battery architecture to maximize range while meeting the power requirements, and a boom-mounted powertrain for easy access and maintenance. Professor Mark Drayler's DAE-11 airfoil was chosen as the only airfoil on both wings. Reasons include that at our range of Reynolds numbers, it has a very high maximum lift-to-drag ratio of about 200. The wings have a relatively high combined aspect ratio of 22.7. This was possible due to the joined wing architecture, which reduces the internal shear forces and bending moments of each wing by using the axial reaction force in each wing to bear some of the lift load. This allowed the required thickness of the internal structural components to be thinner per unit aspect ratio. This aspect ratio was sized to achieve the target whole aircraft cruise lift-to-drag ratio of 25. A stall brake analysis using a non-linear lifting line method and flight testing in X-plane have shown that twist is not necessary for a mild and self-restoring stall behavior. The vertical tail height is primarily sized for the rear wing to fail by buckling and by compressive yield at approximately the same load. It also provides plenty of restoring yawing moments even in the event of a single engine failure during cruise. Finally, the front wing has no sweep and the rear wing has a forward sweep of around 23 degrees, given a decent static margin of 24%. To achieve trim in flight, the front and rear wing incidence angles are set at 4.2 and 1.2 degrees respectively. This also means flow separation happens on the front wing before the rear wing, resulting in a stable stall behavior. Due to the very small constant chord length of 0.485 meters for both wings and the even smaller thickness of 6.21 centimeters, the traditional spar, ribs, and skin architecture was abandoned as a standalone spar cap would not fit easily inside the section. Instead, an alternative structural architecture similar to that found in a helicopter blade is used. The skin is sized primarily for resisting bending moments instead of only torsional shear loads. It also resists shear loads in the chordwise direction. The ribs have been replaced by a solid aramid honeycomb core to resist skin buckling whilst maintaining a light weight. The front wings have a set of yaw axis internal moment resisting spar caps, labeled here as the MTMZ caps, designed to reduce the forward deflection of the wingtips during a positive G load, but also contributing significantly to resisting MX bending loads. The fuselage diameter of 1.8 meters was sized to allow the attendant to comfortably sit next to the patient in flight to perform any necessary life support duties and to ease loading of the patient. The length of 7 meters was selected to provide a reasonable moment arm for pitch control and to provide plenty of floor space inside. There is a 1.2 meter wide main side door for all 3 occupants, and both seats slide forwards and backwards, making the loading and unloading of the patient relatively easy, as shown on the slide in the top right. This illustration shows a rough concept of the fuselage internal structure. The fuselage has a conventional skin, frames, and stringers architecture sized for a 4.1 G positive gust load and a 3 G hard landing. All components other than windshields are made of CFRP. Total fuselage structural weight is 71 kilograms, which is 3.6% of maximum gross weight.
Now for the powertrain design. Thrust for both takeoff and cruise was provided by tilting prop rotors with a 2-meter radius and variable pitch to adapt to changing flight conditions. Their performance for vertical climb and cruise are as follows. To ensure enough power for all segments of the flight, high battery power density was essential. Unfortunately, conventional lithium-ion batteries with higher energy density, or watt-hours per kilogram, have lower power density, or watts per kilogram. This inverse relationship, as shown on the above graph, meant that a single type battery supplying 300 watt-hours would need to be heavier than the entire aircraft to supply enough power for vertical flight. We propose a hybrid high-low power dual battery architecture which would sacrifice some energy density in return for reduced overall battery weight. The batteries are mounted on the prop rotor booms and in wingtip pods. The motor was assumed to have a torque versus RPM characteristic based on the MRAX 268. To ensure both our motors and propellers were running at their respective maximum efficiency, they were matched with a belt reduction drive. To further decrease parasitic power losses, the two foreprops were designed to retract during cruise using an actuator inspired by a wine opener. Linear actuators and a swash plate similar to the flight control mechanism of a helicopter were added to allow for collective and some cyclic pitch control in vertical flight.
Our aircraft's booms needed to house the engines and landing gear, along with the relevant mechanisms. To minimize weight while still meeting the structural requirements of the 3 flight load cases, the boom was constructed from a CFRP Nomex honeycomb sandwich, allowing the booms to weigh only 22.3 kilograms. The aerodynamic cowlings for the front and rear engines were constructed out of thin CFRP plates. With retracted propellers, the estimated drag force on the boom was only 51 newtons. The boom also accommodates the motor tilt mechanism for VTOL flight. The transition process is seen here. The entire boom assembly weighed just 98.5 kilograms.
The landing gears were sized to ensure prop clearance while on the ground, as well as to support loads during a 3G landing, with an ultimate objective to minimize weight. With these in mind, assuming the fuselage and boom gears took 90% of the loads on landing, appropriate tires were selected for these gears, with the fuselage wheel being larger due to its less restrictive side constraint. At the same time, the boom gear legs were sized to maintain prop clearance, and all other legs sized accordingly. The boom gear legs were made of CFRP, and loadings were simulated on these, confirming their ability to resist loads dictated in compliance requirements, along with all other gears.
An analytical stability analysis was performed by modifying equations from Babster for use in a joined-wing aircraft, whilst ignoring the aerodynamic effect of the fuselage and the junction between the wingtips. In terms of static stability, our static margin was 24%, which is quite large, meaning the aircraft will naturally resist changes in pitch. In terms of dynamic stability, the only unstable modes are the phugoid and the spiral, which both have a very high time to double amplitude, meaning that the pilot has plenty of time to notice and recover from these modes.
Our design had to be transferred as close as possible to the simulator. The first challenge we met was the stowage of the front props for cruising flight. Explained as stowage of vectoring engines, however this option works on all engines, meaning that once horizontal cruise flight is reached, all engines would disengage. To solve this issue, we added 2 fixed engines, which act as ghost engines during the vertical flight phases, and switch on to act as the rear engines when the plane is in cruise flight and all the vectoring engines are switched off. Note that X-Plane unfortunately does not hide the vectoring props visually, but does remove any forces coming from the propellers as shown in the right figure, where the front blades exert no forces. With a ready-built model, the team decided to use the progressive flight testing procedure to make sure our estimates were correct. We tested the takeoff, transition, cruise and landing performance separately, and for each scenario we recorded key data such as battery consumption. This was compared with estimates we had made beforehand and saw that they were reasonably close. From this, our range was estimated and a suitable island within this range was chosen. And in our case, St. Martin at 184 nautical miles was chosen. Various test flights were conducted by different team members to remove any effects of piloting style. Finally, the 2-hour-long flight was carried out with an autopilot to reduce the workload on the pilot. Finally, we would like to thank the Royal Aeronautical Society and the Light Aircraft Association for giving us this opportunity. A special thanks also to the organizers which very kindly supported us during the project. We hope you enjoyed our design presentation and we are welcome to answer any questions about it. Thank you very much.